This video relates to material covered in Lecture 1. In this lecture, we begin our discussion of the linear regression model. This model is an important framework for empirical analysis in econometrics and many other fields. As you all know, the linear regression model involves explaining some variable of interest, known as the dependent variable, with a linear combination of other variables, known as explanatory variables or regressors, and an error term that captures unobserved factors. We begin this lecture by illustrating the use of this model to analyze economic questions. This discussion helps us to understand exactly what types of equations fall within the framework of the linear regression model. Then we introduce a set of assumptions about the variables under which we have what is known as the classical linear regression model. We also explore what these assumptions imply about the interpretation of the model. Next up, we formally define the ordinary least squares estimator of the regression coefficients using linear algebraic arguments. We then describe a decomposition associated with ordinary least squares estimation that leads to a measure of goodness of fit for the estimated model known as the multiple correlation coefficient, or familiarly by its symbol capital R squared. Finally, we explore the interpretation of the OLS coefficients. This discussion rests on a famous result known as the Frisch-Wall-Lovell theorem. In this video, we cover the first bullet point. We begin by considering some examples of linear regression models in economic analysis. Our first example involves the so-called capital asset pricing model, or CAPM, which is used to model asset returns. Here, capital R represents the return on the asset in question. Capital R sub F is the risk-free rate, which is the return on some riskless security, typically taken to be a treasury bill if we're using US data. Capital R sub M is the return on the stock market portfolio. So the CAPM is telling us that the excess return on the asset is beta 0 times the excess return on the market plus this error term. This coefficient beta 0 is known as the investment beta of the asset, and it captures the risk associated with holding the stock. The value of beta 0 is very important for investors, as it is an input into their decision about how to construct a portfolio to diversify their risk. A second example involves estimation of the returns to education. Suppose we're interested in learning about how an extra year of education affects the wages received by an individual. To learn about this, we can take a sample of individuals and record their wage, education, and certain other characteristics that we believe may contribute to the wage. Here I've just highlighted one, experience, EXP. Then we might consider estimating a model in which the log wage is explained in terms of education, experience, and we may also include experience squared to allow for the potentially diminishing returns of this variable on wage. Our focus here would be on beta naught 2, the semi-elasticity of wages with respect to education. Our third example involves aggregate production function, here expressed using the Cobb-Douglas functional form. In this model, we're interested in explaining the aggregate production in the economy in terms of aggregate inputs, labor, and capital stock. The parameters of interest here are those on the inputs, and beta naught 2 is of course the elasticity of output with respect to labor input, and beta naught 3 is the elasticity of output with respect to the capital stock. Our last example involves a forecasting exercise. Suppose we wish to forecast the change in price inflation in the economy. We might do so using this very simple example of a time series in model, in which the change in inflation in this period is expressed as a linear function of the change in the previous period. Now, whilst the specific economic question is different in each of these cases, the models we're using here have the same basic structure. In each case, there's a dependent variable that's being explained as a linear combination of some explanatory variables and an additive error term. The key point to note here is that when we say linear, it's referring to the linearity in the parameters, because you notice that the right-hand side in all of these equations involves linear functions of the parameters. However, note that the explanatory variables themselves can in fact be a nonlinear transformation of some underlying variable, such as the log of the labor input, or experience squared. And as we see here, the dependent variable may also be a nonlinear transformation, either the log of the wage or the log of output. In all of these models, the dependent variable is explained by a linear combination of explanatory variables and an error. The dependent variable and the explanatory variables are observed. The error is unobserved by definition. And in each of these cases, we may know the interpretation of the regression coefficients, but we do not know the specific values that they take. For example, in the CAPM, we know beta 0 is the investment beta for that stock, but we do not know the specific value it takes for the stock in question. Similarly, in the production function example, we know beta naught 2 is the elasticity of output with respect to labor, but we do not know what value it takes for the economy. So to use these models to learn about the economic phenomena of interest, we need to come up with plausible values for the betas. To do this, we obtain a sample on the dependent variable and explanatory variables and use this as the basis for our estimation of the unknown beta coefficients. Before we discuss the model and how to estimate the parameters further, I'd first like to say a few words about the types of data that we typically have available to us as econometricians. Economic data typically come in one of four types. The first of these is cross-section data. In this case, all the observations in our sample pertain to the same moment in time. Could be a sample of individuals or households or firms or countries, but the key thing is that the information relates to the same moment in time for each. Second, we have time series data, which involves recording the value of economic variables as they evolve over time. The other two types of data involve combining the cross-sectional and time dimensions. Panel data is the case where you have a cross-section of sampling units that are followed over time. Repeated cross-section data is the case where we take a sample from a population at a moment in time, and then in the next period take another sample from the same population, and so forth. The key difference between panel and repeated cross-section data is that panel data involves the same cross-sectional sampling units, individuals say, but repeated cross-sectional does not. In this course, we're going to focus on the first two. Those of you who are going to take Econ 60052, the microeconometrics class, in the second semester, will study the types of econometric techniques used with panel data and repeated cross-section data. Now, some of our analysis will be generic, but for other parts of the discussion, the data context will matter. And so in those circumstances, I'm going to emphasize the type of data in our notation. So when we want to emphasize that we're working with cross-sectional data, we will index the observations by I, if you like, for individual, and have that index running from 1 to capital N, the sample size. When we are working with time series data, the observation index will be T for time and run from 1 through to capital T. For the first few weeks, the analysis is generic, and so we don't need to make a distinction. And so I'm just going to choose T as the index. But when we come on to talk about the large sample analysis of estimators and inference procedures, then the data context is going to matter, and we will adopt this different notation depending on what context we're working in. To conclude this video, we introduce the generic notation for our model. The dependent variable is going to be denoted by y sub t, that's the tth observation on the variable y. The explanatory variables are collected together in a vector x sub t. The number of explanatory variables will be denoted by k, so xt is a k by 1 vector. Ut is going to denote our error term, and beta 0 is our vector of unknown regression coefficients. So we can write our model out as follows, that yt is equal to xt prime beta 0 plus ut. You can verify for yourselves that if we multiply out xt prime beta 0, then we obtain a linear combination of the explanatory variables with the weights in this combination given by the elements of beta 0. As discussed earlier, yt and xt are observable. The error term is not. The vector of regression coefficients beta 0 treated as a vector of unknown constants that will be referred to as parameters of our model that we will estimate from a sample on y and x. To progress our discussion, it's most convenient to switch to matrix notation. In our specification, we assume this equation holds for little t running from 1 through to capital T. And to emphasize this, I could write out little t equals 1 through capital T on the side here. Equivalently, I could imagine writing out an equation for each observation. So I'd start with y1 equals x1 prime beta 0 plus u1. Underneath it, I would have y2 equals x2 prime beta 0 plus u2, and so forth all the way down to the last equation, which would be y sub capital T equals x sub capital T prime beta 0 plus u sub capital T, giving me capital T equations. Now, instead of writing out this information in that way, I can think of those capital T equations as one single equation involving a vector y and a matrix x and a vector u, where y is a capital T by 1 vector with typical element y sub t, x is a capital T times k matrix with tth row xt prime, and u is a t by 1 vector with typical element ut. As before, beta 0 is our k by 1 vector of unknown regression coefficients. You can verify for yourself that if we multiply out this term, then it delivers the required result. This concludes our discussion of the first bullet point. To recap, we've considered examples of linear regression models in econometrics and used these to emphasize how the adjective linear in the linear regression models refers to linearity in the unknown regression coefficients. We've also presented the model in linear algebra. In the next video, we discuss a set of assumptions that deliver what is known as the classical linear regression model.